You never want to hear about a fire in space, but that's exactly what had to happen for this experiment. The Flux 2 experiment burned fuel droplets to see how they react without gravity. Now, this information could lead to better ways of extinguishing flames in space, as well as lead to environmentally friendly fuels here on Earth.
My experiment is a droplet combustion experiment. We burn fuel droplets in microgravity to understand how liquid fuels burn, so that we can use them efficiently and also cleanly by understanding how the chemistry works. And it has got another application, which is fire safety in space. We burn these things in different environments, reducing the oxygen concentration slowly and then finding out what is the minimum oxygen concentrations below which it cannot burn anymore. So that enhances the fire safety in microgravity environment. Also, we use different diluents in the ambient. So, for example, on Earth you have oxygen and nitrogen, but we can change it into oxygen and carbon dioxide, oxygen and helium. These inert diluents, they change the behavior of how these things burn. For example, in space station, now they use carbon dioxide as a fire extinguishant. So is it the most efficient inert that we can use? So we try different inerts like helium, carbon dioxide, and sometimes also xenon. So this tells us what is the effective fire suppressant in space. So this experiment has got both practical applications, looking at how liquid fuels burn, also fire safety in microgravity. So these are the main applications of my experiments. Earth benefits, we use a lot of liquid fuels in transportation and power generations and so forth. So the objective here is how to use it more efficiently. So these liquid fuels, they have very complex chemical kinetics. So by looking at spherically symmetric burning in microgravity, we can understand the chemistry much better. That means we can use fuels like gas, diesel, aviation fuel more efficiently, at the same time reducing the pollution formation. For example, one of the things that we discovered in the Flux experiments is the so-called cool flame combustion. What happens there is the hot flame goes out and then the droplet continues to burn at a very vigorous rate, but without any visible flame. And it just partially oxidizes the liquid fuel and it extinguishes at some point. This is called low temperature combustion, or cool flame combustion as we call it. And this has got a lot of important implications for Earth applications. For example, the new internal combustion engines that are coming up are being developed. One, for example, this HCCI engine, this homogeneous charge compression ignition engine, which involves low temperature chemistry. So the Flux results will have important applications in that area, for example. And also low temperature chemistry, it reduces NOx formation and soot formation and so forth. So this has got practical applications in the form of using liquid fuels in an efficient and a clean way. And the space applications for this is also very critical, because from the point of view of fire safety. So if you have a firefighting strategy in a microgravity environment or a spacecraft environment, so if you think once the hot flame is gone, then you can't think that the fire is extinguished. What is happening, it's almost like smoldering combustion on Earth. Like if you put a piece of log in the fireplace and the flame goes out, but it can still smolder and produce toxic gases. Just like that, this is the first time anybody has observed this. Hot flame goes out and there is no visible flame, and still the liquid fuel continues to burn, partially oxidizing this fuel, spewing out combustible mixtures. So it is very important to know that. So that in principle, at least we have demonstrated that after hot flame, the cool flame can be a fire hazard, because it can reignite and then bring back the hot flame. So that's a very important space application. And also we have looked at the suppressant effectiveness. Is it CO2 is better, or helium is better, or some other inert is better? So it has got both Earth applications as well as fire safety applications in space.
And that'll do it for us here at the Payload Operations Integration Center in Huntsville. Now back to you at Mission Control in Houston.